Well, thank you very much for inviting me to this conference. Nice. Let me start uh, some introduction in the Isomonodromy-CFT correspondence in general. So. mm, so first, what is the um, what is the essence of this correspondence? It is usually some statement that some expression constructed from conformal blocks, namely some expression of this kind. It's for the original Isomonodromy-CFT correspondence. Mm. It's a linear combination of conformal blocks. This equals to the isomodromic tau function for the linear system with four singularities. So it is associated to the linear system of this kind. So there is a sphere with four punctures. And of the tau function is the following: that d tau over dzi, d log tau over dzi equals to 1/2 trace of this residue at z equals zi. Trace of z squared dz. So there is this, and this derivative is computed on the submanifold with fixed monodromes of this linear system. MIs are fixed. And these monodromies are defined in the usual way, like if you take some contour gamma here, and the compute analytic continuation, let's call it gamma I. If you compute analytic continuation of a solution of this linear system, it equals to y of z times mi. So this is the definition of the tau function, and the definition, and it's not a definition, it's some computation which tells us how this derivatives in positions of singularities act on the linear system itself. And this is what is called by equations of isomodromic deformations. dAI over dzj with fixed monodromies. Equals to commutator of aij over zi minus j. So it's some autonomous version of Gaden system. And this correspondence was found in Gamoun Argovlesovy paper in 2012. And then it had many generalizations, and we will be interested in particular in the Toric generalization. But are there any questions about the statements? Uh, Actually, never thought about this. Oh, I don't know. It would be maybe unnatural to think that these matrices are derivatives of something. No, no, I don't know. Yes, and instead of writing the sum, we can say that sum of AIs equals to constant. So this defines the solution of other A's. Yes, thank you. Yeah, so I want to give some a little bit more conceptual explanation of this formula, which is at the same time a proof of it by Iorgov, Lisovy, and Teschner. This proof goes in the following way. Maybe the idea of this proof is the following. So people like to study on the space of conformal blocks, and if you talk to some mathematicians, they would even call conformal block not some explicit expression which we would like to see. They would call conformal block some arbitrary vector in the space of conformal blocks. And what is the definition of this space of conformal blocks? It's basically the following. So we draw some for example, sphere with and punctures. Maybe we can also choose some non-trivial genus from the very beginning. And we say that this object defines us, so we put some Verma modules here, delta 1, no, delta 0, v delta 1, and so on with delta infinity. And say that it defines us some for the Virasor. Yes, sorry, I didn't say. Say it. In general, this works for arbitrary rank, and the correspondence is the following: if AI is and this Y are matrices 2 by 2 and by n, then it corresponds to Wn. And if n equals to 2, it corresponds to Virasor. And here we'll consider this case. So sorry, I would do this. On which? So here we have isomodromic tau function, which is defined in the following way. We have some matrices in this linear system which are parameterized by monodromy data. So this monodromy data is fixed. And so the system defines some tau function which depends on this monodromy matrices. So the so if you want to write some functional dependence, if you want to write some explicit dependence on some variables, then these variables will be the following. Let me write it here. So this tau is tau of theta 0, theta. Let us choose some points here. This tau is theta t, theta 1, theta infinity, also sigma and eta, and t. So these thetas parameterize eigenvalues of AIs. So AI is conjugate to theta I minus theta I. And we can say the same about the monodromy matrices. So MIs are conjugate to e to the 2 pi I theta I, e to the minus 2 pi I theta I. So it describes the kind of Casimirs, and we also have these two other parameters which parameterize some other coordinates on this modular space of flat connections in this way. Trace m0 times mt equals, well, let us maybe write it this way. M0 mt is conjugate to e to the 2 pi I sigma e to the minus 2 pi I sigma 0, 0. So it is monodromy around these 2 points. So, sorry. No. I should write. Yes. So on the so its parameters are well, so it's actually not quite a function. It is a sanction of line bundle on the product of monodromy of character manifold for this punctual sphere times modular space of such complex spheres. So it depends on a complex modulus T, and it depends on this monodromy data. It's a statement. A definition of the tau function is here, and there is some explicit formula in terms of Virasoro conformal blocks. So if you put charges of this primary fields to be theta 0, so here delta 0 equals to theta 0 squared and so on, like that delta t equals to theta t squared and take some Fourier transformation in this intermediate charge, it will give us this tau function. Which transition functions? Yes, this tau function is defined up to some arbitrary function of monodromies, and this is what I'm going to explain later. Like it is. Yes. So there is a way to fix monodromy dependence of the stall function, and this is precisely what we need to work with this modular transformation of conformal blocks and so on. Hmm? Uh, Sorry, I don't hear maybe the keyword. Uh, hmm? Mm. Oh, could yeah, mm, okay. So uh, now people want to study the space of conformal blocks, and when we write such a picture, it defines us some a map from the tensor product of this delta 0 tensor v delta infinity to numbers. So conformal blocks which depend on complex moduli. Which depends on is such functional which maps from the Swarm modules to numbers. We can denote it by these brackets. It's a kind of procedure of the computation of correlation function, or we can write it in the vertex algebra notation, like that it is something that sends v0 tensor v1 tensor v infinity to as conformal block. Send this vector to a correlator where we have insertion of this y function from the y map from the vertex operator algebra. So So we can write something of this kind. So we kind of insert some fields in these points and compute somehow this homomorphic correlation function. And such a function should satisfy one condition, or maybe better to say the infinite set of conditions that if we substitute the energy momentum tensor and multiply it, let us denote it by sigma gn. If we substitute here the energy momentum tensor under this correlator, multiply it by some homomorphic vector field, which is homomorphic in sigma gn. In the sense, it's homomorphic in this curve without points. So So such expression should be 0 for any epsilon. And this defines some space of functionals, and we can check some things. Then this energy momentum tensor can act on this Hilbert spaces which sit in every point. Like if we write T of z, y of w, and some vector, it will be by definition a sum from n equals actually from some number to from minus infinity to n c minus w to power n plus 2 y of like this. So it defines the action of this energy momentum tensor on any of these Hilbert spaces, and if these conditions are satisfied, we have this abstractly defined space of conformal blocks. And if we try to compute dimensions of the space, we quickly realize that, for example, if it is a sphere with three punctures, then dimension of the space is 1. Sorry. Yeah, yes. So I actually will not use it too much, so I can introduce this notation. It's stupid that I already made this mistake when I was telling precisely this. Uh, hmm? And plus 2, yes, thank you. Yes. Yes, this conformal block, which is the element in the space of conformal blocks, because for fixed Gn. Hmm? No, so here we can only put 3 vectors in this Hilbert space. It means that, well, better to say that we need to, I did not say where to integrate this. It is integral or the boundary of this sigma. So this integral should be understood like this. We take this t of z, move to every of this VLA function, and use this expansion to compute this integral as a sum of residues. So this means, so this integral means in reality that it is a sum of integrals around each point from I equals 1 to n, integral at z equals zi, t of z, this will be a function of zi, vi, something else, epsilon of z, dz. So, and every time we see this, we use this OP of t with y. This is the definition of the action. It is the definition of its action on the states. So yes, we can technically say that it defines what T of z is, and this else satisfies Virasoro algebra. So so is it okay? No. So this way, we can rewrite all these conditions as some equations where we act with some of this Virasoro generator in every point and get get such equations like sum of n terms equals to 0. So there are some linear equations on the space of this functionals on n Varma modules. So, is it okay or not? Okay. So having this definition of conformal blocks, we can then try to construct them in some way. Here, the space of conformal blocks is just one-dimensional. There is nothing to construct. But if we consider, for example, four-point conformal blocks, then the space is already infinite dimensional if you consider arbitrary fields. And one possible way which people usually choose is to say that these conformal blocks are glued from the two pieces, which means that it can be understood like this. So we put here the resolution of identity. So put here V, here some V star, a dual vector, and sum over all this V's which lie in a Varma module with some fixed dimension. V delta, maybe let us write it V sigma squared. So we can check that if we define in the abstract way, if we define such object, then it will satisfy this condition. If the building blocks, three-point conformal blocks, also satisfy this condition. So and this is what is denoted by this letter. So here we have sigma squared. Here we have some theta infinity squared, theta 0 squared, theta t squared, theta 1 squared. So this is what people usually call conformal block. But it is one possible way to define it. And another way to define is to introduce additional object, namely to take such conformal block and insert the degenerate field. So we know the following thing, that if we consider a four-point conformal block with insertion of phi 1, 2, and let us denote it like this. then dimension of such conformal blocks is equal to 2. And here we have the following pictures. We have two conformal blocks in this space. So let us introduce some notation for the central charge, like this. So if we have here some theta 0, then this charge, this is 512. This charge will be theta 0 plus minus beta over 2. This charge will be some theta 1, and this charge will be theta infinity. Now there is this condition for insertion of the generate field. And if we now try to insert it in some bigger conformal block, namely like this. Here, yes, but I don't have a tau function yet. I want to construct this tau function as some special vector in this space of conformal blocks, and it is not in this vector. But yes, it will be defined around this particular point at the boundary of the modular space. No, tau. No, I didn't know. No, but tau is not a flat section of Hitchin connection, I think. But so by a Hitchin connection, you call more or less this linear system, but it is some special limit when everything is holomorphic, right? No. So. But this connection, in some sense, is this isomodromic flow, because yes. So yes. But yeah. Okay. Yeah. So. No, more or less this statement together with with the idea that a correct element in the at least convenient element in the space of conformal block conformal blocks is not this conformal block, but is isomodromic tau function, at least for c equals to 1. So. If we look at this conformal block, let us say that there is some sigma 1, sigma 2, sigma 3, and try to compute analytic continuation of this conformal block in the variable z, where we insert this 512. Maybe I can use the same picture, modifying it. Hmm? It is a position of this extra point. We add one more hole here and insert here 512. So at z. Or in this notation, we can say that it is y of z, comma, highest vector in this degenerate Fermat module, like this. For n plus 1. So I want to take and then we will have another point in this conformal block to define Verlinde loop operators. So maybe we can do it from the very beginning. So it is some n plus 2 point conformal blocks with 512 inserted at points z and w. So is it okay? It's a primary field corresponding to dimension 1, 2. So delta 1, 2 is some alpha 1, 2. So well, maybe it's better to say that it is some field that satisfies a equation like L minus 2 on this vector equals to hmm? Yes. So here we put highest vectors, but not necessarily. Here we can put actually an arbitrary vector. But for definiteness, let us say that those are highest vectors. So yes, yes. Mm. So we know that so it is so originally we have some theta 0, theta 0 plus s over 2 beta, theta 0 plus s plus s prime over maybe minus s prime over 2 beta. So we have such charges, and when we start moving this degenerate fields, we can use some relations that basically come from the study of hypergeometric equation. We can write that such a conformal block equals to sum over s prime equals to plus minus 1, and this s is also plus minus 1. theta 1, theta 0, here is theta infinity, here is theta infinity, minus s prime beta over 2. Times some matrix, which depends on s prime, theta 0. Better to say that it is a function of 2 pi I beta theta 0 e to the 2 pi I beta theta 1 e to the 2 pi I beta theta infinity. And so this reflects the fact that this function is 1 over beta periodic. And this is the local operation. In a sense, we can have arbitrary arbitrary vectors in the Varma modules around these points, because energy momentum tensor is a single valued with any of these fields. And using this local move, we can compute some analytic continuation of this phi12 around the other primary fields. So we can draw a picture like this. When we compute some monodromy around some loop gamma, this conformal block will transform to some expression. So when I draw this, I mean that I will take this degenerate field and move it over some loop, like for example this one. So when we do this, we get a lot of such shifts of dimensions in the intermediate channels. So here we will have some, it was sigma 2 plus, so it will be sigma 1 plus some S1 plus S2 over 2 beta, sigma 2 plus some S3 plus S4, 4 over 2 beta. And here, if we did not touch that other part of conformal block, then they will not be shifted. So then it will be multiplied, so the ZW, then it will be multiplied by some product of this F matrices, also by some, there are also this B matrices, which are just diagonal matrices. Times some B, some matrix elements, and since this matrices depend on e to the 2 pi I sigma, we can write that this function is this whole expression can be written as some matrix M gamma, which depends on e to the 2 pi I sigma 1, and so on, e to the pi I beta sigma 1, e to the 2 pi I beta sigma n, e to the 2 pi I beta d sigma 1, e to the 2 pi I beta d sigma n. Acting on this, this acting on this conformal block. So it contains some shift operators and also some functions of sigmas. And so we get some non-commutative monodromy. Hmm? Uh, on this conformal block, which contains degenerate fields. Sorry, I had to put here this two fields. So let me erase this. So yes. Now we see that if this conformal block with two degenerate fields maps to some this m gamma, which depends on e to the 2 pi I sigma e to the 2 pi I beta sigma beta d sigma on this conformal block. So now we can diagonalize these operators simultaneously in the case when they commute. So I don't want to write them precisely, but they are just some ratios of signs. Hmm? So, so these are the functions that describe this connection formulas for hypergeometric functions. If we normalize hypergeometric functions appropriately, all of them become trigonometric, and this is precisely what is written here. Mm. Oh. Yes, and it depends how precisely we decide to move it, because there is f which translates directly from 0 to infinity, or we can go around 1, then to infinity, and then back to 0. So it depends on the path. But more or less, it is twice, like maybe the minimal choice is twice the number of operators we encircle. Something like this. Uh, so, uh, here we say that when beta squared is equal to 1, then we can say that beta equals to 1, we can say that these operators can be diagonalized simultaneously, which means precisely that we write the Fourier transform. So instead of this conformal block, we say that tau is the element of space of conformal blocks. And this is defined by this formula. Tau is a sum of n less than some z zn a conformal block. Well, Actually, there is some intermediate step. We define a tau function as such a vector in the space of conformal blocks. Mm, Uh, and if you consider this object of the two degenerate fields, then it will equal to the following expression. Will equal to the tau function, if it is z, and this is w, 1 over square root of z minus w, y of that y in the linear system, y of w inverse y of z. And if you want to give some other definition to this tau function alone, without these extra insertions of degenerate fields, we can say that we can construct these two degenerate fields from insertion of the identity operator, which has energy momentum tensor as its descendant. Then move one of them around this Riemann sphere, then go back and project to this identity operator, and this is what people call Verlinde loop operators. So the tau function in this way is defined as is a vector that diagonalizes Verlinde loop operators. And where? No, because we go twice in this direction and then back. And no. Uh, uh, what do I mean? So here we always have a shift by we have two shifts in any channel. We shift when we go in that direction, then we need to go back and we get another shift. So all the shifts are by beta. By some integer multiples of beta, and so is it fine? Not because this appears when we consider this transformation. When we go in one direction, we get one shift by beta over 2, but we should necessarily go back and return to. Yes. Yes. So yes. So this blue path looks like this. We first go to this point, then we use the self transformation to go to this point, then we move here, then we circle around this point. Maybe you can say that we again use the self transformation to jump to this domain. Then make some circle here, and then perform these jumps in the opposite direction. So we use this F transformation twice, when we go here and then when we go back. And this way we get two we get this shift twice. Only M. No, integer shifts because we need to go forward and then back on the sphere. Mm-hmm. Mm-hmm. Oh, do you want to see the transformation of tau itself, or what? Mm-hmm. Oh, but we see that this monodrome is if beta square equals to 1, then this monodrome is do not change when we shift sigma by something, and they are also the same for all descendants. So each term in the sum behaves in the same way. The only thing which we can get some shift of these sigmas, but since we are Fourier transforming, these shifts correspond just to shift of n, which is equivalent to multiplication by eta. No, they can be shifted by each shift is equivalent to multiplication of this whole series by a constant. Mm-hmm. Yes, yes. And this is thanks to the periodicity of all these matrices. Yes. And so one maybe one final thing. Mhm. No. If you put arbitrary coefficients dependent on sigma, if they are not periodic, then different terms will be different. If you shift n by constant, we can get something something different. So. Yeah. So, so now in maybe 1 or 2 remaining minutes, what is special in the case of torus? So in the case of torus, maybe it's precisely this question about integer versus half integer shift. So in the case of torus, we have a transformation which is this one, where we go around singularity and then go back. So in this case, we get, if we put here sigma, we get sigma plus beta over 2. And to fix this problem, we say that actually, conformal, actually we need to combine, so it is sigma plus 1/2. So it changes the sign of monodromy. So to fix this problem, we need actually to consider Virasoro times Heisenberg, which is equivalent to fermion plus fermion. And instead of the degenerate fields, we should consider three fermions: psi 1 2 star, psi 1 2. So this and both of them will have some charges. And maybe I would like to write some formula for the transformation of this tau function. So maybe no, maybe let me better say the main idea of this this modular transformations of conformal blocks. And this idea is the following: that we have conformal blocks which are defined in a different domain of this complex modular space. So we have one conformal block which is defined for tau that goes to infinity. Maybe we can draw it like this a very uh, like this a very long torus. And we also have another conformal block in the limit when tau it is a different tau. It is tau complex. Tau goes to 0, like maybe better to draw a torus like this. And this torus is just rotated. So looking at these pictures, we can say that on the left we have tau function which depends on a monodromies. There is some monodromy MA and MB. So MA, MB. And here we have tau which depends on a monodromies like MB, MA inverse. And we can compute, we can say that now this transformation is something like this. This tau functions are equal by some constant which can be computed. So this modular transformation acting on the space of conformal blocks it becomes just a change of point if we work with the basis of tau functions instead of conformal blocks. And so I don't have time to explain how to compute this function, but it can be done by expressing this tau function as some fractal determinant and the explicit differentiation of this determinant in monodromy data. So this function can be expressed explicitly in terms of monodromies. And so here, instead of some infinite integral with some kernel given by Panzer-Teschner formula, we can get such a simple transformation, which in some sense gives this description as a full description of Morse-Heiberg groupoid for C equals on conformal blocks. But if we wish to get some fusion matrix, we can take this definition of the tau function in terms of conformal blocks and integrate it to take a single conformal block. So we can also get this kernel, but usually it is more convenient to work with such formula. Okay. Okay. Maybe that's all. Could you say? So idea is the following. Maybe I can write this formula. here we had the definition of the tau function by its derivatives, but we can also check that there is a formula of this kind. We can also compute monodromy derivatives of the tau function, and they look like full derivative of the tau function. Plus this Hamiltonian, which corresponds to tau period, plus p d monodromy q, plus sum of theta k's d g k's g k's inverse minus minus a sum of this of these expressions d g k gk inverse for 3-point problems. So we have I need to write the definition of G. The definition of G is the following: AK. So it is a matrix which conjugates A to diagonal form. So which? Hmm? No, it is just a finite sum. 3-point in the case of conform of this conformal block, we have just one 3-point G, which corresponds to this 3-point problem. And that's all. So k equals from 1 to 1 in this case, we can say. So there is the problem on a torus in which we diagonalize this matrix A with some G, and there is auxiliary 3-point problem, which has the same monodromies here and there as this toric problem. So is it fine? No, M and B are monodromy matrices. Yes. No, trace of MA is actually expressed in terms of Franklin-Nielsen coordinate, but so like trace of MA is something like 2 cosine of 2 pi sigma, and trace of MB is sine of 2 pi sorry, pi to sigma minus m over sine of 2 pi sigma e to the 2 pi eta plus, maybe let me write it like this. No, it's have to write another term. Like this, and this is a Franklin-Nielsen coordinate. So, and it is the same eta as in the definition of some tau function. So. Yes. 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 So. Yes. Yes, and it's more or less this function. Yes. Maybe literally. No, maybe up to some. Maybe up to some simple terms, or maybe just this function. Yes. Hmm?